Hello, my name is Pablo and we will present the highlights of our work. Soft error effects on ArmMicroprocessor, early estimation versus chip measurements. Today's trends for microprocessors is to become smaller, denser, and faster, result in a more complex system and in a less reliable device. The reliability threats may come from several sources, and adding protection imposes overhead, so it is needed to choose them as early as possible in a project's timeline, for the redesign is more expensive later on. A lifetime of a product begins in its design, and testing can be done during all its phases, from microarchitecture, RTL, to tests on a hardware prototype. Beam testing on a prototype has the advantage of being very realistic and the testing is very fast. However, if found out that the reliability requirements are not met, the redesign cost is very high. The RTL is also very realistic, but it is slow, and similar to beam testing, it has high redesign costs if necessary. Microarchitectural fault injection, on the other hand, is fast, can be sufficiently accurate, and since it's done early in the project's timeline, it has a low redesign cost. All of these reliability assessment methods have the objective to find the most vulnerable parts and break the fault propagation chain. This chain begins on the hardware and propagates to the microarchitecture and beyond. So, testing closer to the fault source, the hardware, is more realistic but costly. On the other hand, evaluation methods done early are more efficient. Our contribution is to compare microarchitecture fault injection with beam experiments to see how realistic the fault injection is in predicting the fit rate. We also try to differentiate the contribution of software and hardware complexity on the fit rate. For that, we use a standalone ARM A5 and ARM A9 embedded in a system on chip with MVault Linux. The beam experiments were done in two facilities, at ChipIR in the United Kingdom and at Lens in the United States. The A5 comes in a microchip board and the A9 in the Xilinx Zinc 7000 board. Both devices are irradiated with a high flux of neutrons, so the test is equivalent to more than 18 million years of operation. The fault injection is performed on Gen 5 models using GenFin fault injection, with more than 176,000 injections. The fault injection fit rate is predicted using the architecture vulnerability factor with the technology sensitivity, which is measured with beam experiments. We tested 4 benchmarks on both devices with MVault Linux. For our result, we classified them into 3 categories: the silent data corruption, or SDC, app crashes, and system crashes. The SDC is when a program finishes and the system remains responsive, however, the output is wrong. The app crash is when the application stops working but the system is responsive. And systems crash is when the system is unresponsive. Here we can see the results for the SDC fit rate. We compare fault injection and beam experiments and plot the differences. When the fault injection predicts a higher fit rate, we indicate this by a negative number. Positive otherwise, and the magnitude of the values indicates the difference. For example, for the FFT on the A5, the fit rate measured with beam experiments is 1.74 times higher than the fit predicted with fault injection. An interesting result is that for most benchmarks, we have a similar prediction of the SDC fit rate, indicating that microarchitecture fault injection can be sufficiently accurate. Here are the results for the application crashes. It's interesting to see that for the A5, we also have an accurate prediction with and without OS. However, this is not the case for the A9, where we have a difference of up to orders of magnitude. This happens because in a system on chip, most crashes come from parts outside the CPU, which are not modeled in the Gen 5. With system crashes, we have a similar result, with more details in the paper. Moreover, with our evaluations, we can estimate the impact of system-on-chip integration and the OS on the fit rate. We found out that the SDC fit rate is not impacted by the OS or the SoC integration, with increases up to 2 times. On the other hand, crashes are significantly increased by the system-on-chip integration and OS, with an increase of almost 2 orders of magnitude. In conclusion, the combination of both methods provides an accurate and a realistic reliability evaluation. SDC fit rate is not affected by the OS or SoC integration. However, DOE fit rates is significantly increased in the presence of an OS and heavily increases when the system is integrated into a SoC. With fine-tuning, microarchitecture fault injection can provide an accurate prediction for the CPU fit rate early on. Thank you very much for your attention, and we hope you enjoy our work.